Hello guys, so welcome back to our channel Trace Over Time, and this is going to be the third lecture on our series on open quantum systems, and this will be considering the fourth postulate, which is the measurement of our quantum state of our quantum observable. So in the first two lectures we've covered the other postulates of quantum mechanics. For example, the first one was about where my states exist. The second one was about time evolution, and no, the second one was about the combination of our Hilbert spaces. That is, if I combine two spaces, combine two quantum systems, in what state does that exist? And we use the tensor product to define that space, to define those two quantum states and the space that is combined of the two uh, Hilbert spaces, the composite space. The third one was about the time evolution of our quantum state. Okay. So where does my system exist? How do I combine two systems? And the third one, how does my system evolve with time? The fourth one is about the measurement of our quantum state. So this is the most controversial of all the postulates of quantum mechanics. And why is it really controversial? This is something that has bothered all the physicists that since the beginning of quantum mechanics. And some people just accepted it, some people couldn't accept it. The people that couldn't accept it, one of them was Erwin Schrödinger himself, the developer of the Schrödinger equation. He himself was not accepting of this postulate of quantum mechanics, which is why we all know the example of this Schrödinger cat, right? Unless you measure the system, the cat is at the same time dead and alive. So after you take the measurement, the cat is either dead or alive. So the wave function is initially in the superposition of dead and alive. Upon measurement, it's either dead or alive. So that has bothered many physicists all over centuries. And even today, this problem hasn't been really mitigated. One of the biggest physicists of today, let's say Sir Roger Penrose or Gerard Hooft, they also don't accept quantum mechanics. They think that quantum mechanics is incomplete because of this. So you have a certain psi t that's evolving according to the Schrödinger equation, let's say psi t minus I upon h cross Hamiltonian psi t. So this evolution is unitary, but upon the collapse, it will take a certain, let's say you take a projective measurement, it goes to the state psi k. So this collapse is not unitary, and that has bothered physicists over centuries. Okay, and even today, this problem has not been. There is no solution. People haven't found a complete theory for quantum mechanics. The thing is, the mathematical formalism of quantum mechanics, it works everywhere. It's actually, you could say, the most successful theory of all physics, in terms of experimental predictability. Okay. So I'm thinking of making a separate video on quantum measurements by itself. So this will, in this lecture, I'll be dealing with the mathematics of quantum measurements, how you do a projective measurement, how you do a generalized measurement, how you deal with those things. Okay. But the controversy associated with measurements, I'll be making a separate video on it, not a part of this lecture series, but just a general understanding of measurements, of what the issue with quantum mechanics is. I'll make a separate video on it. Okay. So let's start. So today is postulate 4, the postulate of the measurement. Measurement of my quantum system, the quantum state, or say the observable. Okay. So what we do is, let's say we do a measurement of a certain wave function. So associated with that measurement, we have a certain operator, a Hermitian operator, and what will be the outcomes of the measurements? Those will be the eigenvalues of those Hermitian operators. And the psi, the initial psi, will collapse to one of the eigenstates of that Hermitian operator. Okay. So there are certain properties of measurements. So we'll define measurements using certain matrices called measurement operators. Okay. So some properties of those measurement operators would be, let's say this is mk, a set of measurement operators, and k, let's say, goes from 1 to n. Okay, so one property is if I sum upon k, mk dagger mk, that should give me I. So that is actually a derivative of the normalization condition of quantum mechanics. Okay. So let's say we have a state psi that's defined in a certain Hilbert space H. So instantaneously upon measurement, the state psi will collapse to a state, let's say psi k, which will be mk times psi divided by square root of small pk. Okay, so this is my psi k. And what is small pk? That is the probability of finding the particle in the kth state upon measurement. That is given by small pk. And why is it divided by square root of this? For normalization, of course, because summation k of small pk should be 1. That is the rule with probabilities. Okay. So this thing is psi k, and small pk, what does it look like? It looks like this. Mk dagger, mk psi, which you can also write as the mod of the mk psi square. That will also be positive. It will be always positive because the probability can't be negative. So this quantity is always positive. So these are the important considerations of measurements. We are going to keep coming back to these things in all our examples and in all our developments in this lecture. Okay, so let's write this in a certain corner. So let's use a different color for this. Let's say a certain measurement operator is mk. So this will follow the normalization condition. Mk dagger summation mk dagger mk will be I, and the state psi will collapse to psi k. That would be mk psi by square root of small pk, where small pk is psi mk dagger mk psi. Okay, let's keep this in our hand for the following calculations. Okay, so for every observable, let's go to the case of projective measurements. What are projective measurements? So projective measurements are a certain special case of measurements where the measurement operators, which are defined by these conditions. So the measurement operator mk, it has to be Hermitian, and for getting proper, projection operators are useful when in the Hilbert space you have the basis. The basis has to be orthonormal. If it's not orthogonal, then projection operators are not much of a use, which I'll show in this lecture. But let's take a simple I'll take some simple examples to explain the application of projection operators. And the most important thing about projection operators is that it's a Hermitian operator. Okay. So let's say we have a certain observable, and associated with it we have this Hermitian operator A. And we know that a Hermitian operator is a normal operator. We learned this in the last class that a normal operator can be, we can do the spectral decomposition of normal operator, and it could be Hermitian, it could be unitary. We can diagonalize it and we can write it as a sum of its. We can decompose it in its eigenspectrum. Okay. So I do this spectral decomposition of A, and this will give me summation lambda A. Now we will take, let's say, a capital PA, which will look like A. Is get A times bra A. Okay. So these will be my measurement operators. So let's check first. So this PA, does it satisfy these properties? So let's take the first example. Let's say summation mk dagger mk. So in this case, what would be summation mk dagger mk? It would be summation A PA dagger PA, isn't it? Okay, so let's check. It has to come 1. Let's try. So summation A PA dagger PA, that would be P. This is PA. So what would be PA dagger? Capital P. This is again AA. So summation PA dagger PA. This will just be AA times. This is very trivial. I guess you guys already know about all these things, but this is just very trivial. And this is AA. This is just 1 because A is normalized. And this is just summation A get A bra A. So because of completeness of my space, of the Hilbert space. So this is just 1. Right? So we've proved this one. So if we proved this condition of the projection operators. Okay. So this is the only condition actually for being a measurement operator. So we've proved this one. So PA, this projection operator, is a measurement operator, which is defined as this one. Okay. So what will my state collapse to upon measurement? What will be the state that I get upon this projected measurement? So the psi will collapse to, let's say, psi A. And this will be A psi upon square root of small pa. This is the probability of collapsing to the 8th state. So let's what would be the small pa? Again, we'll use this formula: psi pa dagger pa psi. Again, we saw that pa dagger pa is the same as aa times aa, and the a's are going to become 1. This bra a times get a, that's just 1. So again, pa dagger pa, this is pa. Pa psi. Okay. So this corresponding to this for my projection operators, we get this formula. Let's actually write these ones also, because this will also be useful. So this is for the projection operators. So the summation small pk is given by psi pk psi. Okay, and the state will collapse to pa pk psi is another pk. Okay, so let's find what does this give me then. So this is just a times psi upon square root of small pa. The small pa is this. Let's derive it, psi. So this is just aa times psi. Okay, so this is just this time plus times the complex conjugate of this, or this one times the complex conjugate of this one. So this is just mod psi a squared. Okay, so if I take the square root, the square will go away. So no need to write the square root once again. So this will be just mod of a psi. So you see, we have a complex number divided by the absolute value of that complex number. What would that give me? It's like saying so let's say you have a complex number z. So you do the write in the polar form z equals r times e to the power I theta. You divide it by r. So this thing goes away. So what I'm left with is a phase. It's just a phase of unit quantity, of unit magnitude. So this is the thing we'll get here also. We'll get a phase times the eighth state. Okay. So actually we can just try, this is a general consideration, so we can just use this formula forever for projective measurements. So psi becomes a psi k, which is e to the power I theta k times this thing. That's the kth state, whatever. Okay. So we are going to take some examples. Okay, so let's summarize the properties, some properties of the projective measurements or these projection operators. These are also called projectors. Okay. So these are these projection operators. They are the special case of generalized measurements where the measurement operator is Hermitian. Yes. So this is a very important part. Actually, remember this thing. So the special case. Actually, I need to write it, I guess. So projective measurements are a special case of generalized measurements in which the measurement operators say mk are Hermitian operators. Also known as projectors. Okay. So my mk is pk, projection operators. So pk times pl, what would that be? So if pk is equal to pl, so this is kk times ll. Let's think about the form of the projection operators. So this will be 0 if k and l are not the same, but it will be 1 if k and l are the same. So you can use the Kronecker delta function here, k for l times pk. Okay. And then another property is pk dagger is equal to pk, we saw. Then the property is pk square is equal to pk. Okay. And the psi small pk is this one. Probability of finding the state collapsing to the kth state is given by this one, and the kth state will be a phase times the eigenstate k. Okay. So these are certain properties of the projection operators which are very important. Okay, so let's take a certain example. For example, if we take a qubit, let's take an example to understand projection operators a little better. Let's say we have a qubit. This the summation, the superposition of the states 0 and 1, weighted by these probability amplitudes A and B. Okay, where 0 and 1 are just, so A and B are just real numbers. Sorry, it'll be complex numbers, and this psi, it belongs to the two-dimensional complex vector space. Okay, and 0 and 1 are the basis, the standard basis for this space. And in our convention, we'll take 0 as 1, 0. You can actually take the opposite of this, but we're going to take this convention. 0 is, my 0th state is 1, 0, and my 1 state is 0, 1. Okay, so we define measurement operators corresponding to this example. So let's call one P0, that would be 0, 0. You saw that these are the forms of the projection operators. Capital P1, that is 1, 1. Okay. Okay. So this is my M0, my first measurement operator, and this is my second measurement operator, M1. Okay. So we can see that P0 square, what would that be? So P0 square would be 0, 0 times 0, 0. That would be same as P0. And P1 square, that would be 1, 1 times 1, 1. That would be 1, 1. So there is again P1. And P0 times P1, what would that be? 0, 0 times 1, 1. That would give you 0. Okay. Because they're orthogonal, 0 and 1. So these are a set of projective measurements. Okay. So the probabilities of the outcomes 0 and 1 are given as using the small pk here. So small p0, what would that be? That is just psi, pk psi. So this is p0 psi, which we have proved earlier. So what would be psi p0 psi? This one times this one times this one. And if you calculate it, it will just give me mod a square. This is the probability of the state psi collapsing to the 0th state. Okay. And P1 is capital P1 psi. This is mod B square. This is the probability of this state collapsing to the 1st state. And upon collapsing, what would the states look like? A phase times the original state. So the psi would, with this probability, I would get a state which looks like this e to the power I theta a upon times 0. And with this probability, I'll get the state e to the power I theta b is also a phase times 1. So phase times 0 and phase times 1. So one thing that I don't know if you know or not, but as long as this whatever phase you have multiplied with your vector, this corresponds to the same quantum state. Okay. So what does that mean? That means that our state is not uniquely defined by just a vector in the Hilbert space. So if multiply to that vector, you have a certain phase, certain global phase. So these are also different vectors in your Hilbert space. But all these vectors correspond to one state. So we actually call it an equivalence class of vectors. Okay, so these vectors multiplied by any phase makes up a little subspace of the Hilbert space, and this like a little section of the Hilbert space. So this is corresponding to one state, this particular state, and this actually that's why we represent quantum states in the Hilbert space as rays rather than just vectors. So rays are this equivalence class of vectors with any arbitrary phase. Okay. So these are rays, and the rays are the ones that uniquely define a quantum state. not just a vector. That's why we define our quantum states as rays in the Hilbert space. So see, so this theta a could be anything, but it would still mean that I am in the zeroth state, zero eigenstate. Okay. So let's take another example of measuring a certain operator. Let's say. So let's take a qubit again, example. Again, let's take a qubit. Again, the superposition of A0 plus B1. Okay. Now what we're going to do is we're going to do measurement on this system. But what kind of measurement? We know that with measurement we have certain observables attached, and these observables correspond to a certain Hermitian operator. Okay, so let's say we want to measure the spin of the system in the z direction. That is what corresponds to the sigma z operator. Okay, so let's say, so that is 0 1. Actually you can call them as a little 2D, they are defined in the 2D Hilbert space, and they have two possible answers, which are 0 and 1. So it's kind of like a sigma z. You can do the sigma z measurement on it, because same as you do in the case of spin. There are two possibilities, +1 and -1, and you take the spin with respect to the z-axis using sigma z. So we can do the same here using the sigma z operator. So we know that the sigma z operator is the Pauli matrix. Usually we define as 0, 1, 0, 0, -1. Okay. Okay. So what we're going to do is we need the eigenvalues of this. So those eigenvalues correspond to the outcomes of our experiments, right? So what we will do is we do the spectral decomposition of this measurement operator. So the spectral decomposition of sigma z, or we can write z. It is actually +1 times 0, 0 corresponding to this part, and -1 times 1, 1. Okay. So that is the spectral decomposition of my sigma z. And so we can see that the natural projection operators corresponding to this will be P0, 0, 0, and P1 would be 1, 1. So what are the eigenvalues of sigma z here? +1 and -1. And the +1 corresponds to the eigenstate 0, since you see the 0 here. So this eigenstate corresponds to this eigenvalue +1, and this eigenstate 1 corresponds to this eigenvalue -1. But so the outcome, you can get only two outcomes, +1 or -1. So what is the probability of finding +1? Just like we did in the earlier example. So probability corresponding to +1, the eigenvector is 0, and corresponding to 0 state, the projection operator is this one, 0, 0, and so because of that, the state will again collapse to e to the power I theta 0 a, theta 0 1, like we did in the last example, and the probability would be given by this one. So again, the probability of finding, let's say, P0 corresponding to lambda 0 equal to -1, let's say. The probability is given by psi P0 psi, and that is again mod A square. Again, similarly, the probability of finding it in the first eigenstate is lambda 1, let's say, it's -1 +1. Did I mix it up? Oh, this one is +1 and this one is -1. +1 and -1. Yeah. So this is psi P1 psi, and this would be mod B square. Okay. Probability of finding lambda is 1 is this. Probability of finding lambda is minus 1 is this. And the state collapses to these, obviously. The phase times 0, phase times 1. Okay. So this is one example. Let's take another example. An operator, an observable that is more central to physics, more central to quantum mechanics, which is what we do. We take a system, we measure its energy. So what's the Hermitian operator corresponding to this observable energy? We all know it's pretty simple. The Hamiltonian, right? So let's take our Hamiltonian and do the usual recipe like we did with the sigma z operator. We need to express it as its spectral decomposition. Mission A, let's call it EA, the eigenvalues, times A, the eigenstates of the Hamiltonian. Okay. So the EA are the energies, the energy eigenvalues. A's are the associated eigenstates, and the probability of measuring EA would be given by psi, capital PA, psi. Okay, where PA is capital PA is A. Okay, and the psi A upon collapse would be PA psi by square root of small pa, and this is again A psi square root of small pa times A. This is the usual stuff that we read all that we have been learning all this time, and this is just applicable here also. So there is a probability of finding the particle in the Ath state. This is projection operator corresponding to the Ath state, and this is the state Ath state itself. Okay, so let's take a more specific example. Let's take an example where the Hamiltonian is not diagonalized. We'll diagonalize the Hamiltonian and we'll do the spectral decomposition, and then we'll do the usual recipe, applying projection operators to the system. Okay. Let's take the qubit Hamiltonian itself. So it's this h cross, let's say omega x, sigma x, and plus h cross omega z, sigma z. Okay. Well, we're going to put h cross equal to 1. Okay, so let's just write omega x, sigma x, plus omega z, sigma z. This is a Hamiltonian of a qubit. Okay. So omega x, what is omega x? So omega x is defined as 0, 1, 1, 0. Omega, not omega x. Omega is just a constant. This sigma x is Pauli operator, and sigma z is 1, 0, 0, minus 1. Okay. So what we are going to do is we write the matrix. We write the Hamiltonian in the matrix form. So this will look like 0 omega x 0 plus omega z 0 0 minus omega z. Naturally, because of these definitions, so the bigger matrix would be, so omega z here, omega x here, minus omega z here, omega x here. Now we'll have to diagonalize it. We see that this matrix is, this Hamiltonian is not diagonalized because we still have the non-diagonal terms here, and for a spectral decomposition we need to diagonalize it, because 0, 0, 1, 1 we need to, if I need to write it in terms of the projection operators times that one, we need to diagonalize the system. Okay, so how would the diagonalization happen? So if we remember that if I for finding the eigenvalues of this matrix, it would be this determinant of let's say there's an operator A, and then there's the eigenvalue times I to give me 0. Okay, so we need to do this to this matrix. So this will be omega z minus lambda omega x minus omega z minus lambda. So this determinant of this has to be 0. From this we can find the lambdas, and after we get the lambdas we can just write the spectral decomposition after it. Okay, so let's solve it actually. So this is equal to 0. So what that means is this times this things times this things minus this things times this things equal to 0. So that would be omega z square minus lambda square, right? The minus will go in front, and this will be plus. Okay, so minus into yeah, this is correct. Minus omega x square equal to 0. So lambda square would be, this will be plus minus minus plus, and that would be omega x squared plus omega z squared. So lambda is plus or minus square root omega x square plus omega z square. So we got two eigenvalues of our matrix, and let's write them as like this. So e plus minus is give it this name. So these are my possible eigenstates of this system. Square plus omega z square. Okay. Now I can do the spectral decomposition. So spectral decomposition of this Hamiltonian would look like H equals E minus, which is given by the eigenvalue, this one, times the eigenvector corresponding to E minus. That would be like this. This projection operator is associated with it, plus E plus. Okay. So this is my spectral decomposition. Okay. So now we can apply the projection operators. What are my projection operators? These are E minus, and E plus, E plus. Okay, so this is fairly simple. I hope I don't need to write these things again. So you have a certain state, superposition of, let's say, superposition of E plus and E minus. Okay, and with a certain probability, let's say this is C plus and this is C minus, and this is how my wave function is initiated, let's say. So the probability of finding this E plus state would be given by, again, like upon calculating this, we did it for the qubit. So it would give me we know the Born rule, right? So for this, corresponding probability is this one, and for this, the corresponding probability is this one. Okay, and the projection operators were E and E, E minus and E plus, right? So let's say we have prepared the system. Like, how do I understand it better? Let's say I've prepared the system in one of the eigenstates. Let's say the ground state, which is E minus, and now I find the probability. What's the probability of finding the particle in the system qubit in the plus state, E plus state, right? So what would that be? Let's say let's actually measure the formula for this thing. So P plus minus, that would be given by the psi P plus minus times P plus minus and psi. So P plus corresponds to finding the state collapsing to the plus state, and P minus corresponds to finding the particle, finding the system, not particle, I'm sorry, the qubit in the minus state. So this is the formula, and this is just psi E plus minus. These are my projection operators naturally. Psi. Okay. So that is just again the Born rule. Psi E plus minus mod square. Okay, can you see it properly? I hope so. Okay, so this is the probability of finding in plus or minus. Let's say I have prepared the system in plus, so psi is E plus. So in that case, what would happen? Let's say I want to find the probability of finding the particle in the plus state upon measurement. So I prepared the system in the plus state. Now I want to know the probability of upon measuring it, finding the particle in the same state. Okay, so psi is E plus. So E plus E plus. This will be E plus in that case. E plus 1. E plus E plus, that would be 1. E plus mod E plus square. E plus mod square. Sorry. So that would be 1. So that means that if I have prepared, that is the basic understanding of quantum mechanics, that we know that if prepared the system in E1, E plus, so probability of finding it in E plus would be 1. Same way, we prepared it, let's say, in E minus, and I want to find the probability of finding the particle in E plus. Then there will be E plus here, but finding the particle in E plus. I prepare it in E minus. So E minus here, E plus here, 0. So again, we'll get 0. So since these are orthonormal, this is the very important, most important part. These are orthogonal states. If I prepare the system in one of the states, the probability of finding the particle in finding the system in another eigenstate is 0 if they are orthogonal, right? So let's move on. Let's set up this one also for more space. Okay. Okay, so now let's talk about the expectation value of an observer. We have already learned about these things, but in this section there will be an important proof that I'll teach you, okay, which will be useful to the rest of the formalism of open quantum systems. Okay, so what's an expectation value? Oh goodness. Of an observable A, let's say. So this is defined as A psi. This is a general example, not just quantum mechanics. It's just probably this outcome, say lambda A, upon measurement. We know that our outcome is lambda A times probability of finding that in that outcome, the summation of this. So this is the expectation value of A. When you have the state prepared in psi. Okay. So small p a, that is we can write this as summation A lambda A. Again, small p a is given by, in terms of projection operators, it looks like this, right? So we can write it like this, and this psi is not just dependent on A. I can this summation doesn't really bother my psi here, so I can take the psi out and I can just take the summation inside. So I can write it like A lambda A P A psi. Okay. Now what is this? Let's find lambda a, summation lambda a p a. So summation a lambda a p a, that is summation a lambda a times a. If you remember this was the spectral decomposition of a, right? So this is just a. So this part is just psi a psi. So this is just a, so this is psi a psi, right? So this can also be written as this formula. This is trace times a psi psi. So this is a very important form of the expectation value, because we're going to deal with density matrices in the subsequent sections. So in those parts, this formula will be used more, because you can't always get the wave function picture when you have density matrices. When you have let's say states that are not pure, you have mixed states. So the next lecture will be on density matrices, and which will be very useful for, which will be actually the most useful thing for learning about open quantum systems. We have not gone into open quantum systems. We are still isolated from the environment. Our system is still isolated, but when we go eventually, we would need to use the density matrices, and when using density matrices, this formula is going to be more very useful. Okay, so let's prove it. Actually, proof is not important, but just for the sake of just not rote learning stuff, right? We need to know what everything is coming from, not just remembering formulas. So let's prove this one. So trace of yes, a psi psi. Sorry, my chalk. I need to bring another chalk. Wait a second. Okay, so let's prove it. So trace a psi psi. What my formula was? This is the same as psi a psi. We need to prove this one, right? So let's try. Okay. So what we're going to do is, we're going to take this psi, which is our state, which is the state that my quantum system is prepared in. Okay. So we're going to take this psi, and we're going to take the psi as one basis vector for Hilbert space. We define a Hilbert space using psi as one of the basis vectors, and using a certain process. Let's say the Gram-Schmidt orthogonalization process, which we learn in linear algebra classes, etc. Then that you can take one unit vector, you can take one basis vector, and you can make other orthonormal basis vectors out of it, making a certain, following a certain procedure, like like let's say the Gram-Schmidt procedure. So what we'll do is, we'll take psi as one of the basis vectors, and we are going to come up with assuming that we're taking this one as the one basis vector, and we'll make a whole set of basis vectors belonging to a certain Hilbert space using a certain orthogonalization process. Okay. So let's say we make a Hilbert space which is spanned by our first basis vector. Let's call it phi 0, which is just a psi, and then using it we get other basis vectors, phi 1, phi 2 till phi d minus 1, where the Hilbert space is dimension d. Okay. So this is our basis. This is how Hilbert space is defined using these vectors, orthonormal vectors. So let's take the LHS of this, the left hand side. Just trace a psi psi, and we can write it as, so this is my basis now. I can write this trace in terms of this basis. So this will be summation I phi I a psi psi phi I. Because if you know that in the basis phi I, say the trace of a certain operator, let's say O, is just summation I phi I O phi I. Okay, so this is the sum of all the diagonal elements of O. Okay, so this is what trace is. So these are, since these are just numbers, I can change their orders, right? So I can take this one here, take this one there. So this is just I times psi phi I a psi. Okay. So this is my formula. Now you can see that this is a very familiar thing that you keep seeing in all quantum mechanics proofs actually. So this is just the completeness theorem. Since this is a complete, Hilbert space is a complete, and we made a Hilbert space out of these vectors. So this summation will be equal to 1, the completeness theorem. Okay. So this is nothing but I. The I will be gone because of because summation I I. This is identity. So because of this, I will be gone. This part will be gone, and this we're gonna be left with just this. Okay, as simple as that. So we proved it. We took this one and we came up with this one. So this formula for expectation value, remember it. It's going to be very useful in the upcoming lectures. Okay. So now let's talk about the Heisenberg uncertainty principle. Okay, I have to rub this one also, which we've already learned most of the time. I mean, if you're physics students, we've obviously learned about the Heisenberg uncertainty principle, and we're going to prove the generalized version of it, and using certain like a little mathematical proof, but this proof is also important, which I hope you have learned. But still, let's do it again. Okay. So it means that if I have two Hermitian operators, which represent observables, if they are non-commuting, so in that case, I can't measure the two observables simultaneously with exact precision. So that's what the uncertainty principle tells me. So let's say we have two operators C and D. So the uncertainty principle will say that the uncertainty in C times the uncertainty in D, or the standard deviation, they are given as Vw equals to half of the mod of psi commutator CD psi, and that's it. So okay, did I write it correctly? Psi CD psi, and yeah, so that's correct. So this is my general form of the uncertainty principle. So let's prove it actually. So C and D are Hermitian operators. So we can define two more operators like A as C minus expectation value of C, and then B defined as D minus expectation of D. These are all again Hermitian. Both of these are Hermitian. A dagger would be C dagger minus this thing star, which will be the same. So this A dagger will be C minus C, expectation value of C again. So A and B are both Hermitian operators naturally. And now we know that, so what would AB be? AB, if I write the expectation value, this is most certainly a complex number, this quantity. This quantity is most certainly a complex number. So we can write it as the sum of x plus iy, okay, where x is x and y, they belong to real numbers, okay. We can write it like this. And another thing is that 2ab, we know from our experience, the 2ab is actually the sum of commutator plus the anti-commutator. And if you don't remember, commutator is AB minus BA and anti-commutator is AB plus BA, which I guess I'm sure that you already know very well. Okay. So the expectation value of psi with respect to expectation value of the commutator anti-commutator AB is plus psi. What would that be? And if I take the complex conjugate of it, it will be psi anti-Hermitian AB dagger times psi. Obviously. Now what is the Hermitian conjugate of AB anti-commutator? Okay. So that's pretty obvious. But if it's not clear to you, I'm going to show it to you once again. AB dagger. So this is just AB plus BA dagger. So that gives me B dagger, A dagger plus A dagger, B dagger. Okay. Since these are Hermitian, obviously, so this will again be BA plus AB. Obviously. So this is again the anti-Hermitian AB, anti-commutator AB. Okay. So this means that AB dagger, the Hermitian conjugate of AB dagger is the same as AB dagger. So what we'll get is, this will again be psi AB. Now if we do the same to this, the commutator one, we can see that in place of plus here we'll get a minus. In place of, yeah, we got the plus here, but if we take the dagger, the Hermitian conjugate of AB, commutator of AB, we will get a minus in front. This will be minus psi A commutator B psi. Okay. So what does that tell me? Complex conjugate of quantity is the same as that quantity. So it has to be real number. And summation of these will give me 2b. And this AB is this thing. So 2AB will be, expectation value of 2AB will be this one. Okay. So if I compare it, this thing must be the real number. This thing should be 2x. And this thing should be 2iy. Okay. Because the complex conjugate is negative here, this only happens to imaginary numbers, and the complex conjugate is positive here, so this only happens to real numbers, right? So this will be the case. This is 2x and this is 2y. So what would that tell me? That would tell me, I hope you've written it in your notebook. So tell me that 4x squared plus 4y squared, 2x mod of 2x squared plus mod of 2iy squared. So basically this is psi A B psi mod square plus psi commutator AB psi mod square. Now, because of this thing, because of the Cauchy-Schwarz inequality, from the Cauchy-Schwarz inequality, we can write that this is less than equal to, let's say, no, let's actually, we need another step before doing the Cauchy-Schwarz. So this is actually the same as, since we saw that 2AB is this one plus this one, so this will actually be equal to 4 psi AB psi square. Now applying this Cauchy-Schwarz inequality, we get that this is less than or equal to 4. We know that this will be, write it like this. No need of this thing here, of course. And psi. Okay. So what that is, A dagger is equal to A and B dagger is equal to B. So that would imply to me that this is 4 psi A square psi, and this psi B square psi. Okay, because these are Hermitian. Okay. Now A was C minus this thing. I hope you remember the definitions. And B was D minus D. Remember these definitions. So this is just, it's equal to 4 psi, and this is C minus C square psi times this one psi D minus D, and this is squared psi. Okay. So what we've proven is, we've proven that we know that this psi AB obviously greater than or equal to 0. So that would mean, so this one has to be obviously greater than or equal to 0. So this one I can write it as 4, this part psi C minus C whole square psi times psi D minus D square psi is actually greater than or equal to psi commutator AB. It's greater than or equal to psi and this is the same as the mod of psi commutator CT psi square. Okay. So we have actually proved it. So what is this? This is this, and this is this. And what is this? This is this part. Okay. So we have proved the Heisenberg uncertainty principle using this formalism, this mathematics. Okay. So this is one of the most useful, one of the most fundamental principles of quantum mechanics, uncertainty. So if you have two observables represented by two Hermitian operators and they don't commute, so there is a limit to how certainly you can measure them simultaneously. If they don't commute, then you don't have to worry about that thing. If they, I'm sorry, did I say the opposite thing? If they don't commute, so the commutator is 0, then you use the Heisenberg principle. If they don't commute, then there's a limit to how accurately you can measure them simultaneously. Okay. So let's go a little deeper into the case of measurements. So I told you that projective measurements are a special case of measurements in quantum mechanics, and these operators, these projection operators, these are Hermitian, and these are useful when our Hilbert space are the basis of our Hilbert space. They are orthogonal. They're orthonormal. What if they are not? Then we have to make use of certain other kinds of measurements by the name of positive operator valued measurements. So I'll explain it to you with an example. Okay. So the example is pretty interesting. It's like a thought experiment. So let's call it Alice. Alice's unknown state. Okay, let's give it this name. Why did I name it like this? So let's say we have a friend Alice, and she has given you two states. Okay, and you don't upon measurement. I'm sorry. Fuck. Let's say we have a friend Alice, and she has given you a state psi, and there is a probability of finding the particle of the state to be in two possible states. Okay, let's say she has given you a state psi, and it will either be psi1 equal to 0 and psi2 the square root of 1 over square root 0 plus 1, which is also known as the plus state. So she has the system is either in this state or this state. So Alice has given you this state, and you have no idea which one of these states it's in. Okay. So first thing we can notice is that these are not orthonormal, in the sense that these are not orthogonal, right? So you take the scalar product of psi1 and psi2, and you can get a non-zero number, even though these are different states. Okay. So what the rule of this game is, we know that it is one of these two states. It is either this one or this one, but Alice is not telling us what state it is in. So our task is to perform measurements, decide which one of these two states were given. Okay. So we are not allowed to make any errors in the identification. Okay. Our answer should be distinct. It's either this state or that state. Okay. So these are the rules, and both states must be treated equally. Okay. We cannot preferentially identify only one of the states and proclaim ignorance on the other one. So what is our strategy? So these are not non-orthogonal states. Okay. So let's try with projective measurements. Okay, let's take our measurement operators mk as p0 and p1, and p0 is 0 0 and p1 is 1 1. Okay, so let's say, what are the possibilities? Let's say if Alice has prepared the state in psi1, then what is the probability that I will find 0? Okay, so probability that I get the outcome 0, taking assuming that Alice has prepared it in the state psi1. So this will be given by psi1. This is my p0 projection operator corresponding to 0th state psi1. So we'll get, obviously, psi1 is just 0, so 0 0 0 0. p0 is 0 0. So this will be just 1. So if Alice is prepared in this state, then obviously I'll get 0. Probability of me finding the 0th state is this one. So now let's say Alice is prepared it in psi2. let's say Alice has prepared the state in this state, then what is my probability of getting zeroth state? So this will be given as the probability of finding outcome 0 with assuming that she has prepared it in psi 2, that is given as psi 2 p0 psi 2. What would that be? Do I need to calculate it for you? Let's do it. So psi 2 p0 psi 2. The psi 2 is this bra is just 1 by square root 2 0 plus 1, right? So just the bra of this, and then p0 is 0 0, and psi 2 again square root 2 0 plus 1. Okay, let's apply these things to 0 times 0 is 1 0 1, this is 1 by square root 2, 0 times 0 1, 0 times 1 0, so we get half. We get these two results, so this is half. So what does that tell me? It tells me that if Alice has prepared it in psi 1, I could get 0. Obviously I'll just get 0, and if I get 0, it could be that Alice has prepared the state in psi 2 also, because psi 2 is the superposition of 0 and 1. So if I get 0, I have no information of which state Alice has prepared the state in, because if I get 0, it could be either in psi 1 or in psi 2. But another thing to notice here is that if you get 1, that is only present in psi 2. Okay, so if you get 1, you can be sure that the state was prepared in psi 2, not in psi 1. So in this case, you have understanding about the system. You got useful information upon measurement. But in the case of this 0, you don't get. So what's the issue here? The main issue is that the two possible states that we were given initially in the beginning, so these are not orthogonal. So projection operators isn't giving me the whole story. So if I get 0 upon measurement, it could be that the state was prepared in 0 or the superposition, any one of them. So in that case, we are going to make use of a different kind of measurement called a POVM. So what are POVMs? Let me give you a little bit of a example. I'll come back to this problem after explaining to you what the POVM is. Okay. So let's say you have a certain generalized measurement operator mk. That's right, POVM. So POVM means positive operator valued measurement. Okay, so let's say you have a certain measurement operator mk, and the mk's, and you define an ek, which is mk dagger times mk, and ek has to be a positive operator. Okay, so what is a positive operator? Positive operator is something that always has non-negative eigenvalues, and the expectation value will always be positive. Okay, so let's see the properties of ek. So ek dagger would be, so mk dagger times mk dagger, and this is mk dagger. This is just mk. I'm sorry, this will be the opposite order because we're taking Hermitian conjugate. So first we take the Hermitian conjugate of this, so mk dagger times mk dagger plus dagger. So this is the same as mk dagger mk. So what we've proven is, so ek dagger is the same as ek. Okay. So so it means that since ek dagger is ek, so the POVM elements, these are not the, we defined these operators ek. These elements have are actually Hermitian. Ek dagger has to be equal to ek. Okay, and the expectation values would be positive since this, we have defined like positive operators. So let's say we've been given a certain set of positive operators ek, and can we define measurement? Can we define the POVM? Like, can we use them for measurements? Any arbitrary set of positive operators ek with the property that this thing is equal to. So uh, since ek dagger ek is mk dagger mk, we can see that these properties will it will look like summation of mk dagger mk k. This is just summation of k ek. This is I. So this is the corresponding property for POVMs. Okay. This is an important identity, important formula that we need to remember for the case of POVMs. Summation of ek has to be 1. Okay. And EKs are positive operators, and they're Hermitian and all that. So let's say we have been given a certain set of positive operators, and we want to define, we want to do measurements with those operators. Can this be done? Actually, the answer is yes, because any positive operator, any normal operator, they can be represented in a polar decomposition. So uh, let's say we have an operator A, right? We can do a polar decomposition on this, which means that I can write this as a multiplication of this u times p. So u is an unitary operator and p is just a positive operator. Okay. So what does this do? So you can imagine it as this. So this is an operator that a linear operator. What it does is, let's say we have this space. So let's just take the example of this 2D space, 2D Cartesian coordinates. This is x, y. So let's say we have a certain vector here. What a certain operator can do is, it can take this operator. Let's say it has a magnitude 1. It can take it from here to here. Let's say we've changed the magnitude, we've scaled it by a certain quantity, and we've rotated the vector by a certain angle. We can, so this rotation is represented by this unitary operator. Okay, and this scaling is given by this positive operator. So you can imagine it like this. So this is what an operator, linear operator, does. You can do it, you can write it as a polar decomposition, which is, you can say this space has been rotated and stretched. So by rotating and stretching, you can define any this thing, linear operator. So P. So you can choose the P in a certain way. Let's say we've chosen the P as the square root of a dagger a. So what does that indicate? So this is a certain P. That what it does is, it will just stretch it along the coordinate axis. Let's say 1. It will stretch 1 to here. The stretching will be only along the axis. It will be just pulling or pushing like this along the axis, not any other direction. So this is represented by this P equal to square root of a dagger a. Okay. So if the operator A is invertible, then we can write it as U as A P inverse. Okay. So in our case, what will happen is, we can, so if it's P is, if the P is ek dagger ek, let's say, so we can define the for every k we can we could use the given POVMs. Okay, so we have the element ek which I have already explained to you, the summation Ek for POVMs, that would be 1, and Ek is Hermitian and all that. So we can do the polar decomposition and we can define a measurement using that Ek, which was given to me like an arbitrary Ek. We can write it like this: UK times square root of Ek. Okay. Why square root of Ek? Because mk dagger mk is Ek was if you remember, Ek was equal to mk dagger mk. So if I write mk dagger mk here under the square root, it will become Ek. So this is how we can write it. So if we define an Ek, right, a certain way such that the summation of Ek for k equal to 1, this UK, we have total right. We can choose UK according to our choice, because this just represents that the phase, the state of a system remains the same. It doesn't matter what phase it. I mean, what global phase is attached to it, right? So it's irrespective of the phase, it's the whatever vector it represents the same state. So this is actually this idea is represented by this UK here in the case of POVMs. So the psi will collapse to a state psi k, which will look like UK square root of Ek by the probability of finding this in psi k. Okay, so this is, upon doing the POVM, we'll get this state where Pk is just psi mk dagger mk. So Pk here would be just small k here, small pk here would be Ek psi. So this is just mk dagger mk. Okay, so this is what a POVM is: positive operator valued measurement. Now let's go back to the example where we were given a state where there was two possibilities, but we don't know which state Alice has prepared the state in. So there were two possibilities. One was 0 and then another one was the summation, the superposition of 0 and 1, equal superposition. So the plus state, 1 by square root 2, 0 plus 1. Okay. So let's use POVMs to get a little better answer about Alice's state, I mean, upon measurement. So with projection operators, the problem was that if I find the state in 0th state, so it means that it could have been either psi 1, it could have been 0, or the superposition of 0 and 1. By getting the outcome 0, we couldn't tell it by ourselves that it was in psi 1 or psi 2. So by measuring psi 0, we didn't get any information about the state that Alice prepared. So this time I'm going to do this POVM. So for POVM, we have to choose these EKs, right? So using the UK, we saw that MKs will be UK square root of EK. So we can choose these EKs in an intelligent way so that they can be used for measurement. So let's say we make an intelligent choice, and that would be E1 as, let's say, alpha 1 1. Alpha is just a constant, and E2 is alpha 2 2. Oh, sorry, there is a 2 here. It's let's say minus. Well, minus is square root 2 and 0 minus 1. So this is a minus state, and let's say E3 is I minus E1 minus E2. Why is that? Because we need to satisfy the summation rule, the normalization rule for the EKs. Summation EK k goes to I. Okay. So that is why we defined another probable outcome corresponding to E3, that is I minus E1 minus E2, such that the sum equals to 1. So let's using this, let's compute the probabilities of all the 3 possible outcomes. Okay, so let's rub this. Actually, we should write it in a corner so that we can refer to it while explaining. So E1 was just alpha 1 1, E2 was alpha minus E3 I minus E1 minus E2. Okay, so if I get, let's say, 1, if I get the outcome 1, okay, so how, using POVMs, how would I say that the probability of Alice to have prepared the state in psi 1? So that would be, in the language of POVM, small p 1 psi 1, it would look like psi E1 psi 1 E1 psi 1. What would that be? Okay, so let's remember the size. So psi 1 was 0, and psi 2 was the square root 2, 0 plus 1. So let's find it. So this will be over square root 2, 0 plus 1 times E1. E1 is just alpha. Let's take the alpha outside, and 1 1 and psi 1. Again, 1 over square root 2. Psi 1 is, no, psi 1. So this is for psi 2. I'm sorry. Let's calculate for psi 2 first. Okay, so psi 2 is, let's say the state is prepared in psi 2. The probability of finding 1, the outcome, my outcome is 1, but the state is prepared in psi 2, as given by this. So let's calculate this one first, because I wrote it already. Sorry, a mistake. I should have written psi 1 as 0. So let's just calculate this one first. Okay, so this will be 0 plus 1. What would that give me? So 1 1 times this thing. This is this bracket here. Yeah, 1 1 times this thing. This will only pick the 1 here, and this will pick another 1 here. So that will give me alpha by 2. Okay. Similarly, if I take this is what we are going to do. So this is probability of finding the outcome 1, such that, I mean, assuming that the state Alice was prepared it in psi 1. So that would be psi 1 E1 psi 1. Okay. So this is 0. What is E1? E1 is alpha, E1 is 1 1, and this is 0. So this is clearly 0, right? So what did we find? Let's summarize our results. Actually, using this kind of calculation, you can find all the probabilities. So let's list them. You can do the calculations by yourself, because all of these are just the same. Okay, so let's say you have the outcome 1. So let's say probability of Alice has to have prepared this in 1. We found it. This was psi 1 E1 psi 1. That's the recipe of finding this probability, and this was 0. And probability of finding the particle 1, let's say prepared in psi 2, is psi 2 E1 psi 2 equal to that was, we got it as alpha by 2. And let's list down all the possible outcomes. Psi 1, that is psi 1 E2 psi 1. If you do the calculation, it will come as alpha by 2 again. Now probability of if you find the particle in state 2, The probability of the state was prepared in psi 2 is and it is psi 2 e2 psi 2, which is again 0. Okay. Now we have, since you have this E3 also, this third possible outcome, you have to find the probability of this one also. So this will come as, you know the formula, this will come as 1 minus alpha by 2. This will also come as 1 minus alpha by 2. Just do the calculation and you can find it. So what does this tell me? Let's say I have found the outcome 1. Then I can be sure that the state was prepared in psi 2. Okay? Outcome 1 corresponding to this EK. These will be my, for POVMs, so these are going to be my outcomes, right? So let's say we get the outcome corresponding to E1. So I get outcome 1. So for outcome 1, the state that the probability that the state was prepared in psi 1 is 0, and we are sure that the system was prepared in psi 2. Same for outcome 2, we are sure that the system was prepared in psi 1, right? If we get 2, then we are sure that it was prepared in psi 1. But what about outcome 3? Okay, so if we get the outcome 3, we see that this probability is the same depending on this number alpha. Probability is the same for the state to have been prepared in psi 1 or psi 2. So how do we deal with it? So what we do here is, these alphas, these are 1 minus alpha. We do it in a certain way that we minimize the alphas. Actually, so keeping E3 positive. So E3 is a positive matrix, and we use the property of the positivity of the matrix. So using that, what we do is this unknown constant alpha, we minimize the alpha, and we, with the constraint that E3 has to be a positive matrix. So using that, if we do this, you can get the value of alpha, which is square root 2 upon 1 over 1 plus square root 2. Okay, so this is a POVM. So this is what this was much better than using projection operators, because in the projection operators, if after doing the measurements, we were not, in one case we were sure that the system was in the second state, psi 2. But if you got 0 state, then we couldn't be sure that whether it was prepared in psi 1 or psi 2. So that was because the two possible states, they were not orthogonal. So if in this case, if the states are not orthogonal like this one, I can use POVMs. So here my advantage is, if I get this outcome 1, I can be sure that the state was prepared in psi 2. And if I got the outcome 2, I can be sure that the system was prepared in psi 1. And these outcomes are represented by these matrix elements, these elements E1, E2 and E3, which are my POVM elements. You can say that these are POVM elements, and they are represented as MK dagger MK. Okay. So what did we learn today? We learned about the positive operators. We learned about POVMs measurements. We learned about projection operators, and we did some examples to show you about projection operators, the usage of projection operators, and we showed you an example of POVMs as well. Okay, so thank you for watching. So this ends the postulate part of the review of the postulates of quantum mechanics part. The next part will be about density matrices and a little beyond that. Okay, so thank you for watching.